Hi, we're Tyler, Matt, and Everett, and we'll be teaching y'all about Chapter 8.1, Binomial Distribution. And so the first thing you need to know about binomial distribution is what binomial actually means. And the bi stands for two outcomes. It's either a success or a failure. Nom stands for a fixed number of trials, and as the number of trials increases, you can start to treat it as a normal distribution. The I stands for all trials are independent, so you have to make sure that they all fall into the independence clause. And then all stands for all outcomes have the same probability. So you don't, say you have a deck of cards, if you take one out, you have to replace it rather than keeping it out of the deck. The notation of binomial distribution is B and P, where B stands for binomial distribution, N stands for the number of trials, and P stands for the probability of success.
The formula for a binomial distribution where exactly k successes in n trials occurs is equal to n over k times p to the k power times 1 minus p to the n minus k power, where n over k is not n divided by k, but instead it is n factorial over k factorial times n minus k factorial. For a little formula practice, we just have a little question that we can practice plugging into our equation. Everett is an 80% free throw shooter. What is the probability that Everett makes exactly 5 out of his next 10 free throws? All right, so we've got Px is equal to 5, because 5 is the number of successes we're looking for in this problem, is equal to 10, the total number of trials, over 5, times the probability, 0.8, which we get from him being a 80% free throw shooter, to the 5th, times 1 minus p, 0.2, and 10 minus 5 is 5, so that's also to the 5th power. This, like we said before, is just the top number factorial over the bottom number factorial times 10 minus 5 factorial.
Now we're going to talk about binomial mean and standard deviation. And basically the mean is just the expected counts. And so that means that mu sub b is equal to n times p, n being the number of trials and p being the probability. The standard deviation, which is equal to sigma, is n times p, or the square root of n times p times 1 minus p. And once n times p and n times 1 minus p are both greater than or equal to 10, you can treat it as a normal approximation instead of using binomial, so you can just use your normal test like you would on any other thing. If you want to use the normal distribution approximation, you still have to use the binomial mean and standard deviation like you would if you were going to treat it as a binomial distribution.
All right, here we got a practice problem. TZQB is a 442 hitter. What is the probability that Z gets 16 hits out of his next 30 at-bats? What is the probability that he gets no more than 16 hits in his next 30 at-bats? And what is the probability that he gets more than 16 hits in his next 30 at-bats?
Now we're solving for the probability that Z gets 16 hits in his next 30 at-bats. So P of x equals exactly 16 equals 16 over 30 times 0.442, which is the probability, to the 16, which is k, and 1 minus p, which is 0.558, to the 30 minus k, which is 14.
First, we're going to calculate that Z gets exactly 16 hits in his next 30 at-bats. So how we're going to do that on the calculator is we're going to go to options, statistics, distribution, binomial. All right, now we're going to use BPD, which is the probability that he gets exactly 16 hits out of his next 30 at-bats. And then in the parentheses, it goes KNP, K being the number of successes, 16, out of 30 at-bats, and P is just his batting average, which is .442, we execute that, we see that the probability that he gets exactly 16 hits in the next 30 at bats is 0.08755.
Next, we're going to do the probability that Z gets no more than 16 hits in the next 30 at bats. And we're going to take the probability that we just did, which is the probability that X equals 16, and you're going to add all of the possibilities that are less than 16 all the way down to 0. So what this ... stands for is plus the probability that X equals 15, plus the probability that X equals 13, 14, and all the way down to 0, which is 0 over 30 times 0.442 to the 0 times 0.558 to the 30.
Next, we're going to calculate the chance that he gets 16 or fewer hits. So 16, 15, all the way down to 0. The probability of all of those added together. Same thing, options, stats, distribution, binomial. Now we're going to use BCD, which calculates less than or equal to the K value that you plug in. So same thing, it's going to be K and P. We're going to go 16, comma, 30, comma, 0.442. And the probability of him getting 16 or fewer hits is 0.88288.
Lastly, we're going to do the probability that Z gets more than 16 hits in his next 30 at-bats. And what you do is you just take 1 and subtract it by what you did in the previous problem, because the probabilities always add up to 1. So all you have to do is subtract this from 1, and that'll give you the probability that X is greater than 16.
All right, now we know that all the possibilities add up to a total probability of 1. So to find the probability that Z gets more than 16 hits, all we're going to do is 1 minus, and then same thing as up here. We're going to do 1 minus the probability that he gets 16 or fewer. So 1 minus BCD, 16, comma, 30, comma, 0.442. That gives you 0.11711 probability, or 11.7%.